The research paper presents a theoretical framework for detecting Majorana Zero Modes, MZMs, in a Kitaev chain of semiconductor quantum dots embedded within an InP nanowire, in proximity to a P-wave superconductor. This system is subjected to an external magnetic field, which spin polarizes the lowest conduction spin level and the highest spin valence band level of each dot. The Kitaev Hamiltonian is used to describe the hopping and pairing of electrons in the conduction band levels, with the chemical potential tuned to bring the chain to near half-filling in the absence of superconductivity. When a photon with energy close to the band gap of an ASP illuminates the dots, it generates a hole in the valence band and an electron in the conduction band. This leads to the formation of exciton Majorana Fermion complexes, resulting in distinct signatures in the absorption spectrum of the chain as a function of photon energy. The paper outlines the exact diagonalisation method and the Majorana and bond fermion representation of the Kitaev Hamiltonian, providing insights into the optical signatures of MZMs in the absorption spectrum. The study concludes by summarizing the results and discussing potential experiments for detecting Majorana fermions in a semiconductor Kitaev chain. This work contributes to the ongoing efforts in realizing synthetic topological quantum matter with topologically protected quasi-particles, with potential applications in topological quantum computation. The study of Majorana Zero Modes, MZMs, in a system of quantum dots is the focus of this research. A Hamiltonian, comprising three parts, is used to describe the system: He for electron interactions, HH for hole interactions, and HINT for electron-hole interactions. The electron and hole parts are modeled using tight-binding models, while the interaction term captures Coulomb attraction between electrons and holes. The system's behavior is probed through an absorption experiment, revealing peaks in the spectrum corresponding to the formation of bound states involving MZMs. The Kitaev Hamiltonian is also explored, highlighting its role in supporting MZMs and introducing the concept of bond fermions. By employing exact diagonalisation methods, the authors compare energy spectra in both normal and bond fermion bases. This comparison underscores the utility of the bond fermion basis for further analysis, providing a valuable framework for understanding MZMs in quantum dot systems. The authors introduce the exact diagonalisation method for determining the energy spectrum of the Kitaev Hamiltonian, spanning the system's Hilbert space with a configuration basis. Each configuration is represented as a product of creation operators acting on the vacuum state, resulting in 2n possible configurations for a system with n spinless orbitals. Eigenstates of the Kitaev Hamiltonian are constructed as coherent linear combinations of electronic configurations with different electron numbers, and the Hamiltonian is applied to obtain an eigenvalue equation. Due to the parity symmetry of the Kitaev Hamiltonian, matrix elements are non-zero only if the electron numbers have the same parity, breaking the Hilbert space into two decoupled subspaces of even and odd configurations. The authors then express the Kitaev Hamiltonian in terms of Majorana and bond fermions. Electron operators are rewritten in terms of two Majorana fermion operators, which satisfy a slightly different anti-commutation relation than ordinary fermions. The Hamiltonian is rewritten in terms of Majorana fermions, revealing the pairing between Majoranas of different types in adjacent sites. However, the Hamiltonian is not diagonal in Majorana fermions, so they are not quasi-particles of the Kitaev Hamiltonian. To address this, the authors define a new set of fermionic operators, bond fermions, constructed from two Majoranas of different types from adjacent sites. These bond fermions are created by combining creation and annihilation operators of adjacent sites. This transformation allows for a more insightful understanding of the Kitaev Hamiltonian and its quasi-particles, providing a foundation for further analysis and exploration in the field of quantum computing and condensed matter physics. The Kitaev chain is represented using bond fermions, which are operators that describe the Hamiltonian. In the topological regime, the zero mode plays a crucial role. Bond fermion configurations are essential for the exact diagonalisation of the Kitaev Hamiltonian. The authors stress the importance of conserving parity in the bond fermion numbers, which leads to the splitting of the Hilbert space into even and odd subspaces. This conservation of parity is essential for accurately capturing the physics of the Kitaev chain. The energy spectrum of a chain of n equals 3 quantum dots is presented, showcasing the effectiveness of the bond fermion basis in describing the system. The bond fermion representation allows for a more intuitive understanding of the Kitaev chain's behavior, particularly in the topological regime. By leveraging the bond fermion basis, the authors demonstrate the possibility of exact diagonalisation, providing a powerful tool for studying the Kitaev chain. The energy spectra of the Kitaev chain in both the normal and bond basis are characterized by distinct configurations of bond fermions as eigenstates of the system. A doubly degenerate ground state emerges, accompanied by singly excited states. Doubly excited states also play a significant role in the energy spectrum, contributing to the overall structure. In the context of the Kitaev chain and light-induced valence hole absorption, photon absorption injects an electron-hole pair into the system, which is relevant to the subspace of all configurations with one hole. This process is crucial for understanding the interaction between light and the Kitaev chain, particularly in the context of quantum computing and spin-liquid states. The refined summary maintains the technical accuracy and depth of the original content, ensuring that the key concepts, methodologies, and findings are preserved while presenting them in a concise and direct manner suitable for voiceover narration. The research analyzes the absorption spectrum of a chain and the optical signature of the Majorana Zero Mode, MZM, by examining the Hamiltonian with one hole in the configuration space of bond fermions. The Hamiltonian is diagonalized exactly for an electron-hole system. For n equals 3 dots, configurations are listed, including even and odd configurations of bond fermions with one hole. The whole Hamiltonian is represented by a constant, mixing states with the same electronic configurations but different hole locations. The full Hamiltonian structure is detailed, including the interaction term that mixes different bond fermion configurations. The energy spectrum of the electron-hole system shows a branching into two groups for bonding and antibonding pairs of states as the electron-hole interaction increases. The energy spectra of the full Hamiltonian with one hole in the even subspace are illustrated as a function of electron-hole interaction V, for n equals 3 dots, with increment equals tand micro equals 0. This figure compares the cases of localized and mobile holes. For a localized hole, there are 4 states associated with each dot, resulting in 4 pairs of doubly degenerate states, evident from the peaks at EO and E plus or minus, where EO corresponds to the middle dot's excited state and E plus or minus are the transitions involving the end dots. In contrast, the case of a mobile hole shows a split of degenerate levels into sets of triples, corresponding to the 3 propagating modes of the hole band, leading to additional peaks in the absorption spectrum. This setup enables a detailed analysis of the energy spectra and its dependence on the electron-hole interaction. The absorption spectrum of a chain of quantum dots with a localized hole is calculated in the topological regime, where the superconducting gap increment equals the hopping amplitude T, and the chemical potential micro is 0. The polarization operator P creates an electron-hole pair along the nanowire, while its spatially resolved counterpart P, I, enables the creation of such a pair on a specific dot I. The absorption spectrum A, E, is derived as a sum of contributions from each dot, comprising even and odd parts corresponding to different ground states. In the case of a localized hole and zeroed triplet pairing tau, the full Hamiltonian becomes block diagonal, simplifying the expression for A, E, as a sum of individual dot contributions. The paper further explores the decomposition of an electron created at site I into a superposition of creation and annihilation operators of 2 bond fermions. The interaction V-Na-in mixes these bond fermions, which is crucial for detecting the optical signature of the Majorana Zero Mode, MZM, in the system. This analysis provides a critical step towards identifying the optical signature of the MZM, a key feature of topological systems. By understanding the absorption spectrum of quantum dots in the topological regime, researchers can gain insights into the behavior of exotic quasi-particles, such as the MZM, which have potential applications in quantum computing and spintronics. The spatially resolved absorption spectrum for a chain of arbitrary length n, with a focus on the case of n equals 3, is discussed in this section. The concept of bond fermions and their role in shaping the absorption spectrum are introduced. An analytic expression for the absorption spectrum is derived, revealing peaks at E0, E+, and E, each with distinct characteristics. Notably, the peak E+ is more easily resolved and serves as a better optical signature for the Majorana Zero Mode, MZM. The presence of the zero mode can be determined by the visibility of a peak at high energy near E+ when probing the end dots. This underscores the importance of spatially resolved absorption spectroscopy for detecting MZM, offering an advantage over scanning tunneling microscopy approaches. The absorption spectrum of a quantum system with mobile holes exhibits a complex pattern due to the system's dynamics, leading to multiple transitions. This complexity is in contrast to localized holes, where the absorption spectrum is simpler. Comparing the absorption spectra of mobile and localized holes, additional peaks emerge in the former, as depicted in figures 6 and 7. These spatially resolved spectra highlight the significant changes in the system's behavior as hole hopping increases. The zero mode, initially confined within the chain ends, begins to leak out, becoming a robust signature even under varying hole hopping parameters. Understanding these dynamics is crucial for future studies and applications in quantum computing and information processing. The leakage of the zero mode from the chain ends indicates the potential for more efficient information transfer and manipulation within quantum systems. This could have profound implications for the development of quantum algorithms and quantum hardware. In conclusion, the absorption spectrum of a quantum system with mobile holes presents a rich landscape of transitions, revealing the intricate interplay between hole mobility and system dynamics. This research provides valuable insights into the behavior of quantum systems and paves the way for further exploration in the realm of quantum computing and information processing. In the context of semiconductor quantum dots, the theory of Majorana excitons interacting with Majorana fermions in a Kitaev chain is explored. The research confirms the existence of non-local bond fermions with zero energy, a crucial prediction in this field. Furthermore, the study predicts interband absorption spectra, which can be experimentally verified. Notably, the authors propose that spatially resolved absorption spectra can be employed to confirm the localized character of Majorana Zero Modes. This is a significant finding, as it provides a potential experimental pathway to verify the presence of these exotic quasi-particles. The work has implications for future research on hybrid nanowire systems, where the interplay between Majorana fermions and excitons could be harnessed for quantum computing and spintronics applications. The research acknowledges support from various programs and grants, highlighting the collaborative nature of this work. In the appendix, detailed calculations for a chain of length 3 are provided, including the matrix elements of the Kitaev Hamiltonian. These calculations serve as a valuable resource for researchers seeking to build upon this study. The Kitaev Hamiltonian matrices for the even and odd subspaces are derived using equation 8, resulting in matrices Heaven and Hod, respectively, as shown in equations A4a and A4b. These matrices are expressed in a specific ordering, similar to that in equation A3. Notably, when increment equals t in micro is 0, the two Hamiltonian matrices become diagonal. In Appendix B, an analytical calculation of the absorption spectrum for a localized hole is presented. For a chain of arbitrary length n, and with increment equal to t and less than 0, and micro equal to 0, the two degenerate ground states of the system are expressed as Gs and Gs, as defined in equations B1a and B1b, respectively. The absorption spectrum is derived using the ground state, Gs, with a similar procedure applicable to Gs. The coefficients Cj are expressed in terms of the creation and annihilation operators Aj and Aj, as shown in equations B2a and B2b. For 1 less than j less than n, the action of Pj on Gs is calculated, resulting in equation B3, which is used to find the excited states. The eigenstates of the full Hamiltonian H, including the excitation energy 2, T, are then determined, yielding the eigenvalue equation B5, with two eigenstates, A minus J, J and A plus J, J, corresponding to energies E0 and E1, respectively, as shown in equations B6a and B6b. In the context of quantum computing and topological quantum computation, the full Hamiltonian H is analyzed, where H equals He plus eta minus V nay. The authors leverage Majorana Fermions, a crucial component in topological quantum computation, to derive equations for eigenstates and their corresponding energies. The matrix elements of the Hamiltonian H are first discussed in the basis of two eigenstates, N1 and A1, 1, which are related to the original ground state, Gs. Through equations, B7, and B10. These matrix elements are then expressed in terms of a plus or minus, as shown in equation 18c. The authors proceed to calculate the expectation values of the number operator N1 in the new eigenstates A-1, 1 and A plus 1, 1. Using equations B11 and B10, they find that the expectation values are given by 1/2 A minus and 1/2 A plus, respectively. This result is consistent with the result obtained in equation 17, for the case of 1 less than J less than N. The analysis of the Hamiltonian H and the derived equations for eigenstates and energies provide valuable insights into the role of Majorana fermions in topological quantum computation. The calculation of expectation values of the number operator N1 in the new eigenstates sheds light on the properties of these states, which is crucial for understanding the behavior of quantum systems. Quantum materials are studied for their electronic and magnetic properties, crucial for advancing technologies. Research focuses on electron behavior in quantum dots, graphene properties, and the magnetic properties of specific materials. Further investigation is necessary to fully utilize these materials' potential.